Alright, back with another video, and this time this video is going to be on rational expressions. So, first things first, let's talk about what is a rational expression. Well, first question you have to ask yourself is what's an algebraic expression? And we all know what an algebraic expression is because it's just a polynomial. If you're still wondering, anything that looks like that. So it could be something that looks like that. Polynomials, you have stuff like x plus 1. Any of those are algebraic expressions. Next, we ask ourselves, what's a rational number? Now, I've said before what a rational number is, and I gave you the simplest definition possible. It's basically a fraction. So, it's a quotient between two integers, a fraction, and that's just what a rational number is. The key word that gives it away is right there, ratio. So let's keep on moving. So since you know what an algebraic expression is and a rational number, a rational expression is just a fraction with polynomials in it, or the quotient between two fractions. That's all it is. So since we covered that, it looks something like that. You have a polynomial in the numerator and a polynomial in the denominator. If we keep going, what we're going to be doing with these rational expressions is simplifying them. So given any rational expression, say any rational expression or any rational number, say for example here 15 over 20, this can be factored, right? So we factor 15 into 3 times 5, and you can factor 20 into 4 times 5. And notice what you have now is the 5 times 5. So that cancels, right? And what you're left with is 3 over 4. So the same idea can happen with rational expressions. You factor it, and you try to find something that's in the top with something's in the bottom. It's actually what you're looking for is your greatest common factor, which is what you'll naturally get if in fact you factor a polynomial, if in fact there are any. So if in fact we took that as we can factor this, common factors, these terms have an x in common, right? And these have a 4 in them. So we factor out an x in the numerator, we factor out a 4 in the denominator, and what we're left with is an x minus 2 here and an x minus 2 here. We cross those out, what we're left with is x over 4. Let's try another one just so we can really get a good idea. Let's try this rational expression right here. It says x squared minus 3x over x squared minus 9. Now, we do the same thing. We factor it, and then we look for the GCF between them. So if you factor this, notice between here and here, they both have an x in common. So you can factor out an x in here. This is just difference of squares, isn't it? So you have a perfect square, and subtraction sign in between them. So when we factor it, it looks like that. Here in the bottom you get x plus 3 times x minus 3. In the top you get x times x minus 3. So since you have an x minus 3 in the numerator, x minus 3 in the denominator, that cancels out as well. So since that cancels out, what we're left with is x over x plus 3, right? So pretty much that's how you simplify them. Very simple. Of course, they're going to get a little bit more complicated, but the idea is easy. Let's try this really large one just to see if, in fact, we can really do it. Notice in the top that it's not really common factor. There's no common factors. It's not difference of squares, so we have to actually do quadratics to factor the top and to factor the bottom. When we factor the top and factor the bottom, we end up with 5a minus 1 times a plus 1 in the numerator and 5a minus 15 times a plus 1 in the denominator. We already see a greatest common factor. We see a common factor between the numerator and the denominator. Also, we want to make sure that things are fully simplified. So notice inside these parentheses, there's still a 5 in common right here. So at the same time, we want to factor out that 5. And now it's fully factored. So once it's fully factored, these cancel out. And what we're left with is 5a minus 1 over 5 times a minus 3. Now notice there's nothing else to be factored when we're totally done with it. So that's the whole idea behind it. If in fact we keep one more idea that I want to talk about is rational functions. We understand like what a rational expression is. So what a rational function is just a rational expression with that f of x in front of it, which makes it a rational function. Now remember, when we actually dealt with functions, what we had defined, we had defined domain of functions when we were doing functions. And when we were actually doing polynomials or polynomial equations or so, we had defined roots or zeros. Well, when we were doing polynomial functions, we had to find the zeros of those functions when we were actually doing them. So the idea is almost the same. For domain, remember what domain is that all possible values, right? So I'll write all possible values right here, right? And what the zeros are, or the roots, is wherever the function itself, f of x, is going to equal 0. So in order to find that, notice in rational functions, the thing that will stop this function from being defined is if you have a 0 in your denominator. So if in fact you're looking for domain, what you want to do is set your denominator. Your denominator cannot equal 0. So you actually want to solve that equation for it not equaling 0. And once you solve that, you'll be able to find out what your domain is. Now, the thing is, to find out what your zeros are going to be, or your roots, what you want to do is you want to set your numerator equal to 0. And that will actually give you your roots of the function, basically where the function is going to equal 0. First off, what you want to do is you want to factor it. You want to make sure it's fully factored so it makes life easier. We did this a little bit in polynomial equations. So now, if in fact we don't want our denominator to equal 0, so if we don't want our denominator to equal 0, to actually find the first thing, which is domain, then we know that our domain in this case is going to be all values of x. Well, let's start it off and let's actually solve it now. Wait, let me erase that. Let's solve it now. Notice here that x plus 3 equals 0. Your denominator will be 0 if x plus 3 equals 0 or x minus 3 equals 0. So in that case, that means that your denominator would be 0 at x equals 3 or x equals negative 3. Now remember, we don't want our denominator to be 0, so we don't want x plus 3 to equal 0. We don't want x minus 3 to equal 0, so we don't want x to equal 3, and we don't want x to equal negative 3. So if that's the case, our domain will be all values of x such that x does not equal 3. And wait, let me get some of this stuff out of the way so I can see. X does not equal 3. Oh, that's a lot. And x does not equal negative 3. So boom, that's our domain. For our range, well, I'm sorry, not for our range, but to find the zeros of the function, we're just setting the function itself equal to 0. So if in fact we set the function itself equal to 0, you'd multiply the denominator to the other side, that becomes 0 anyway. So really, that's just setting the numerator equal to 0. So actually, trying to find b, you want to find out where x minus 8 equals 0. And that means that x equals 8. So zeros of that function would be x equals 8. And the domain will be all values of x such that x is not 3 and x is not negative 3. So we'll do more of these in class, but this is the idea of rational expressions, simplifying rational expressions and rational functions. I hope this video wasn't too long. and I'm gone.